So, Alice and Bob,
Yes.
go right ahead.
Can you design and implement a class?
Sure, I can do that. I'm an object-oriented guy.
Great. In that case, design and implement a few dozen classes that interoperate closely, call to each other's methods consistently, and collaborate to implement complex algorithms. But make sure we can test each one independently, defer configuration decisions until the last minute, and then let hot swap changes when we change our minds again. And I want it all to be easy to maintain with minimal documentation.
I might need some help with that.
Oh, fine. Spread responsibility for classes across the whole team, but make sure that no one is ever blocked on anyone else. And I'd like some concrete ways to measure progress, even though no individual part of the design makes any sense without the whole.
Bob, this is your line. Okay. So, dependency injection is basically a gateway to doing all of those things if you use it well. It is actually two different concepts. It's a design pattern, an OO design pattern, and on the other side it's also a development technique. So the main focus of the pattern itself is to facilitate loose coupling. We're going to talk more about what that is in detail. And to extract from an object-oriented program a more formal definition of what the inter-object mechanisms are. And this is where object-oriented programming languages tend to fall down. They're great at constraining the states and behaviors of individual objects, but when you start talking about how objects collaborate to get things done, the language doesn't really provide you very much help. So this is a way to begin modeling that in a more rigorous way. This idea that because we have defined the boundaries between the modules better, we have the possibility of actually unplugging and replugging them without stopping. You can also talk about the way that your project moves as it matures, crossing over these boundaries, achieving these interfaces. And it's a way to actually meaningfully describe the maturity of your development project. On the technique side, it really comes down to you have to design for it to start with. This is not one of these things we can add later. So sort of like multi-threading. We can't just design the whole program and then add multi-threading later. It's going to change the way you do your construction and test phase. It kind of injects this new idea of integration and documentation as a phase. It alters configuration and deployment because of the interface and modular concept. Those interfaces also become ways of monitoring what's going on with your program. And as has been mentioned, Spring and other tools exist to help you do all these things. So that's a lot for one tech talk. So I'm going to do about half of each of those. In fact, half of each half. And we're going to really focus on design because the tools and libraries and all these other things can really only help you if the design is oriented toward the notion of injection to begin with. However, we will talk, I've got like one slide at the end where we're going to talk more about the dynamic side of it. So let's talk about modeling. We've got a module here called company. It's got two classes in it. They've got a one-to-many relationship. That's that little crow's foot there is actually a database thing. Read away from the block. So each department has many employees. Each employee has one department. And then they've got all this behavior. If you look in the call-outs, department has methods that call methods of employee and vice versa. So the two of them are going to ping-pong back and forth in order to compute something like pay on the department side. So that's clear enough. I think this would be an easy module to write, relatively easy module to test. It's small. Where is the interface between department, and employee. Where is that? Where's the mechanism between them described? Yeah, it isn't. It has melted. It has effectively diffused into the behaviors of the two classes, and this is what we would call an algorithm leak. The individual algorithm for computing pay has effectively just bled all over the place. And so maintaining it means chasing it all around. And that sensation in your head that you get when you're following an algorithm as it ducks in and out of different objects is the source of the phrase spaghetti code. But, this one's small, we can cope, right? So, before it was just department and employee that were tightly coupled. Every call back and forth like that is actually like a stitch that's sewing these two guys together. Now we've got a bunch of them involved in coupling. So where are all of the inter-object mechanisms now? Every intercardinality represents one, and there are actually a couple of skip levels. Department depends directly on project. Assignment depends directly on project for a couple of things. So this leads directly to death by coupling. Coupling is contagious. Dependency is transitive. And if you don't figure out a way to break it, then the module will just grow forever. And you wind up with a module with every class in the program in it, and no particular way to use any one of them without all the others. I can't test it. And the wonderful thing about this is that you wind up with the surface area to interior volume ratio problem. There are so many crossovers between biology and computer science. As it gets bigger and bigger, it kind of starts to collapse because you have less and less surface area to get at the internal state through. So how do we fix this? Well, if you're an arthropod, yeah, if you're an arthropod, then you just start perforating yourself. But let's see if we can do better. So, how many people here sit and think real hard about the module dependency graph in their project?
I don't think I actually think about a graph, but I think I think about what you're doing.
Okay, so if I've got a module that imports stuff, A imports stuff from B, and then later on B imports stuff from A, either directly or through some more meandering cycle, does that cause you to break out in a sweat, or are you okay with that? No, well, you know the story about, I'll give you $10,000 to put a drop of poison in the reservoir? It's one tiny drop. It won't even kill one fish. It won't hurt anything. It's harmless, except that I'm meeting with everyone today and making the same offer.
Slippery slope.
Yeah, and there's also another interesting study that I like to talk about in design scenarios. So the government spends money on building housing projects, affordable housing, subsidized housing. And they're nice. They're built nicely and they're well designed. And then somehow or another, they turn into slums. How does that happen? So the government spent money to figure out how this happens. And the answer was one broken window that was left unfixed for too long. And it sent the message to the people who lived there that no one cared if the window was broken. So, we're social creatures, and programming on a team is a very social thing. It's one of the most intensely social things people do. It's this very precise and rigorous form of creativity, and we all have to do it simultaneously. It's hard enough to do it by yourself. A cycle in the dependency graph is like a broken window. It's fine as long as you go out of your way to point out that you did that, and that you're not sending the message that we don't care. that it's okay to start stitching everything together into a mass. So the main issue here is that the dependency cycle means that things that are presenting themselves as two or more separate modules really aren't. Right? The cake is a lie. Because you can't use them separately, you have to use them all together. You can't test them separately, you have to test them all together. So even if you do write it as separate modules, you're really just making yourself feel better. It's one semantic thing. Keeping the dependency graph in your head, or better yet, on paper, and making sure that the reasons for the way it's laid out are documented, you'll find as you do that, it actually starts to form tiers. That you can sort of partition your graph into meaningful layerings and things like that. That is the foundation on which you build stuff. And as you test, as you build this thing up and build new on top of confident old, you build a quality system. And this is really the definition of a quality software engineering process. You can't test quality in at the end. You have to be aware of what you're doing as you do it. So if you find that there's a cycle in your program, and I'm willing to bet, go back to any program of any non-trivial size that we are using, and you will find them. It is usually a strong indication of a design problem. And what you have to do is cut it apart. So the question is, where do you cut? So this is an interesting subject. I had originally thought that the notion of entity strength was something that was fairly commonly known, and it turns out it's really just a database-ism. So is this something you guys still talk about as DBAs?
What?
Entity strength, relative strength?
No.
Okay. So in the database world, a strong entity,
Has a different term.
a strong entity is one that can form its own primary key. Right? A weak entity does not have identity of its own except in the context of some other stronger entity. So in other words, it has a partial key and a foreign key. Right? So my invoice has all these line items. The invoice has a unique ID number, and then the line items are just sequence numbers within that. Right? So the line items are weak relative to the invoice. This also comes up in languages that have garbage collectors. If you have a strong pointer, it makes you weak relative to the thing you're pointing at, because you need that thing to continue to exist. Somehow, you are contributing your state to its state. Weak pointers actually don't make you weak. It's kind of, because you don't care if that thing's there or not, right? Or if the pointer is unmanaged, then it doesn't necessarily make you weak. Strength is relative. You always have to talk about it in context of two things that are interacting. So if the individual line item had separate charges, then the line item is strong relative to the charges, but it's weak relative to the invoice. So why is this important? Well, a module is usually defined by a single strong entity squatting in the middle like a spider, and it's surrounded by its weak hangers-on as your injecta. So what you should be shooting for is that the weak things depend on the strong ones, but not the other way around. So let's take a look at this again. So one-to-many relationships like that, usually a very good sign that the one side is strong. It's not 100%, but it's pretty close. So in this case, department deletes its employees when it goes. Lifetime control is a very strong indication of strength relative. So it's okay for employee to depend on department because it's the weaker one. The problem is that department is depending on employee. That's the cycle. So we want to break it like that. So now what was one module has become two. In the department module, we have a mock, our employee, which is just the parts of employee that department cares about. Right? So calling it a mock is a little bit confusing because in more general terms, a mock represents a public interface that is commonly known, lots of people can depend on, and we can swap it out. Like, I'm going to mock the database API or the file system API. In this case, it's a much more specific thing. This is the department's version of employee. Not everything, just the stuff the department cares about. So now, when we write a unit test, for example, for department, which we do, right? We can provide a test employee that lives within the unit test module and can be used to drive department through its various states that we want to test. And once we're satisfied, we can build a real employee in a separate module that will extend the mock and fulfill its contract. So in terms of dependency, employee module depends on department module, and that's all. Doke. So
That's just like referential integrity in a relational database.
that's correct. Well, referential integrity is mitigated by foreign keys,
Right.
which bring about weakness. So there you go. These concepts show up all over the place, right? It's in language design, it's in the management of your heap, it's in the management of your database. Booch, arguably, one of the original formulators of object-oriented theory, said that objects are defined as chunks of data that have state, behavior, and identity. As it turns out, he's slightly off base, right? Because it doesn't have to have an identity to be an object. But to be a reference type, it does. Its identity matters. And as soon as you bring identity into it, you start to talk about this notion of strength and weakness. So, all right, what about this? This is another piece of the other diagram. In this case, assignment is certainly weak, but it's weak relative to two things. Right? So it's co-owned, shared, fought over. And in most cases like this, what you're actually looking at is a many-to-many relationship between employee and task. And this is a coordinating entity that we're going to use to store attributes of the association itself. Right, so it is super weak. Right? It really just represents this connection between these two. And as such, you're going to see tangles of dependency in algorithms where employee needs information from task, so assignment goes and gets it, and vice versa. Right? So you're going to be chasing all up and down this thing. So how do we split it? Got to break both legs. So in this case, we have, sorry, Nisha. Not you personally. There's this abstract notion of an assignment that everyone in the village can agree on. Right? Everyone knows assignments have names or hours or something, whatever it is. Everyone agrees. Anything like that can go up there in the abstract assignment. But then we get down into stuff that only employee cares about or only task cares about. So we wind up specializing the general assignment into these subspecialties that just deal with the local dependency. And then in the end, the real assignment, the one that we instantiate, is going to be a mix. Right? So in object-oriented terms, this is close to a mixin model. In Java, we would do this with interfaces with, and this is your implementing aggregate. Right? So we aggregate the real assignment, and then we can delegate the interfaces that we have extended to it. So this gives rise to a very neat way to organize your projects. I don't necessarily advocate this, but it's a great way to do it if you start off this way and can keep it up. You've got a directory of your abstracts, just pure interfaces that describe your entities. And then you've got a directory of your various points of view on those guys where we have all of the inter-object mechanisms well defined. And then we have a directory of the final implementations. And we use abstract factory patterns to construct the right kind of thing. But we always refer to it through its abstract interfaces. So it's a really tidy way to run a project, and it makes it very clear at what level you're thinking. you're up there in the abstract directory, you're the lord of the system, you're deciding in these very broad sweeping terms what all these concepts are and what they do. And then you start in the mixing directory, you start looking at specific ways these guys interact, and you're pinning them down, right? And then really, in final implementation, all you're doing is dotting the I's and crossing the T's. So, what about that? One-to-one relationships are a bugger. They frequently revolve around equal strength, and in a lot of cases, it's actually one object that you have managed to separate. So first strategy is maybe this is one class. Let's try to conflate it. Not always possible, particularly where there's an inheritance going on. So splitting this is the most work. Here's an example of the three-layer thing I was just talking about. So we've got abstract A and abstract B. And our mixing models that specifically work out what their mutual relationships are, and then the final versions. But look, even though it's a little bit complicated, the graph is not. Right? So these arrows are where your problems lie. If you have a cycle there, you're in trouble. There are no cycles here. And even though it's a lot of individual pieces, what you have here is a place for everything and everything in its place. There's a very specific place in the layout of the code where you will address each kind of issue. There's a very specific place, therefore, where you will test it. Okay? Hi. It would be great if you would go forward. There we go. So I talked about this a little bit earlier. I like visuals, so this one will help to sort of solidify the concept. When you've got a module that's just full of internal complicated state and has a tiny little interface to get at it all, you have a ship in a bottle. Compiler is a great example. We put a string in, a string comes out, and in between, unbelievably complicated things happen. But the only way to drive the compiler through its states is to stick a string in there. Right? You've got one API call to try to get to every state. Imagine you were trying to do code coverage. How would you manage, even with perfect white box knowledge, to get at every little nook and cranny of the ship when you can just reach to that tiny little neck with tweezers? Right? You should be thinking in terms of Legos. You want your pieces to be all one color, homogeneous, almost entirely made up of their interface. That's your best shot at reuse, it's your best shot at testing, it's your best shot at not winding up with hidden state. By the way, if you want to really, really test your knowledge and skills at getting through code coverage, try covering all your exception paths. It's actually not that bad when you've got all these mocks, right? Because I can inject all kinds of bad data into my department, for example. I can put all kinds of broken employees in there and trigger every exception path. So why do all this? So earlier I said that not all of you were in the room, but I couldn't decide whether the thrust of this talk was going to be on whether you should do this or how you should do this. And I decided on how, because I think too often design talks are a bunch of thou shalt nots and not a lot of sort of prescriptive advice on how to solve problems. So I wanted to focus on that. But looking at those giant diagrams with arrows flying all over the place, you can sort of say, I still have a deadline. I still need to get things done. Your progress is much more visible in all those little pieces than it is in the ship in a bottle. So in terms of career management, you will be seemingly more productive engineer because you will actually be a more productive engineer. Isolating everybody's work through these interfaces keeps you from blocking on each other. I abstractly know what Kevin's component's going to do, and he abstractly knows what mine's going to do, so we don't actually need to wait on each other. Knowing when these abstractions become testable is a much more meaningful way to track your project's maturity than just saying how many hours you have left on something, right? What can it do? Out of the design, you can just sort of think of like the little boxes lighting up, which bits are currently working. These interfaces are places where we inject pre and post conditions. Right? This is designed by contract. I can enforce, in some languages, that, and in others it's a little harder, not just that the API call has certain types or whatever, but that we have certain predicates that have to be satisfied, and if somebody violates them, we catch them in the act as they cross the frontier from one module to another. So we can catch that in unit testing. We can catch it dynamically. The injection frameworks in many cases allow us to monitor the data that goes back and forth over these interfaces. Isolating your work down to the smallest piece. This is actually another important point where medicine comes in. So we have to do surgery on someone. So just start cutting somewhere, right? Surgeons work very hard at isolating the specific thing they're working on. The euphemism they use is gaining hemostatic control, which means this person's not going to bleed to death. You want to create your stage, right? Pin out just the thing you're going to work on, isolate it from every other possible issue so that the project doesn't bleed to death while you're trying to do this piece of surgery. In practice, it's also going to let you go faster because your edit, compile, test cycle is tiny, especially if you're mocking out the stuff that has a long startup and teardown. If you guys are programming anything in Hadoop, anything where you're talking about a big MapReduce running across the framework, those things take hours or days sometimes, right? And if you're waiting to find out your program is wrong, it is really bad for productivity, right? Because you don't know when the pipeline's going to complete, so you start working on something else, and then you get interrupted. And so making sure that that cycle goes fast, protecting your productivity by isolating yourself, big deal. Another interesting point, documentation. All of those interfaces can be commented, and along with the preconditions and postconditions is a pretty good stand-in for good documentation. Right, what are the expectations here? So even if we don't, if we're extreme programming, which means not paying attention in many cases to keeping up with the documentation, or just accepting that we never do anyway, at least forcing yourself to comment your interfaces is a reasonable compromise. But mostly, these things are your test harnesses. That's your biggest issue. So let's look at that. For some reason, every dependency injection example online talks about this particular example, so I figured what the hell. So we're going to write an expert system that's going to trade stock. It's going to be connected to a banking system, it's going to be connected to the stock exchange, and we're just going to plug it in and turn it on, because we should be able to get this right the first try, and even if we don't, we can just unwind those transactions and everyone will be cool. No. So mock out the areas where there's high risk, where you really, really want to test it. In this case, the stock genius is this algorithmically dense expert system. I really want to isolate just that thing. And I want to be able to provide it with a variety of test inputs so I can get 100% code coverage in there. And there's one other benefit. The adapter pattern. So we don't have control over the entity that's actually going to provide us the banking interface, right? That's Chase or whoever. But we also don't necessarily want to build our stock genius to talk directly to Chase or to talk their particular kind of banking API. So the mock is actually an opportunity to create an adapter. So we have maybe a whole series of them for the different banking institutions that translate the stock genius's needs into what that bank can do, and vice versa. And then, if our needs change, we change the adapter. If the bank changes, we change the adapter. We're isolated on both sides. So I told you I had one slide on this. Everything we've done so far has been static. At the time that we compile or run the program, all the final types were known. But as those of you who use Spring and Juice and HiveMind and a bunch of others know, that's not necessarily the only way to fly. Once we are well isolated, we can choose to dynamically defer the decision about the final class until runtime. So this allows us to use an injector, a container, change out implementations, make rolling changes to the servers. When we do an upgrade, we can let old classes live out their usefulness and replace them with instances of new classes over time. You can do hot swaps and failovers and plugin architectures and all kinds of goodies. But it's totally useless unless you've already designed for it. Right? We can't. There's no amount of intelligence in Google Juice that's going to inject stuff for you. Right? All it's doing is automating what you've already done statically. So 90% of the battle happens before you get this far. All right. Last slide. I've been talking for a while. This is your most important thing. You don't remember anything else. This is what you really need. Be aware of the dependency graph. It does matter. It is the thing that, when it degenerates, changes your beautiful high-rise apartment into a slum. The question is, what's the difference between a dependency and a dependency cycle? I'm repeating for the recording. It's the same as the difference between an edge in a graph and a cycle in a graph. It's okay for A to depend on B as long as B doesn't depend on A, or through some chain depend on A. And so I can take a dependency, and then this is actually two different ways of doing things. If I have a well-established module A, I can build straight on top of it. Right? Build module B, just take a dependency. I could also choose to mock out B anyway. Right? Especially if what I'm really trying to create is a point of articulation in the design. Even though B is well established, even though B is been here since day one and we've tested it to death, I want to be able to just talk about the services and aspects of B that I care about, so that if we ever change, I have this ability to remain isolated from that change. So it's your choice whether you want to take a direct dependency or inject a mock. But sometimes you don't have the choice. If there's a cycle, then you have to inject them.